All right, welcome to the velocity level analysis part. And so we have we had left off after we've derived PL1 and PL2 last time, and in the off time I plugged them into the Newton-Raphson algorithm, and I just plugged in the results that I got right here. So theta 1 turned out to be a half radians. Theta 3 turned out to be 0.324 radian. D4 turns out 221.044 millimeters. And D5 turns out to be 343.61 millimeters. And that ends the position level analysis. Okay, so to do the velocity level analysis, we need to go back to our vector form of our loop equations right here. I defined, I designated them by the symbol star. And we will take the time derivative of these equations in star in the zeroth frame. Now, it is very important to remember that when we are taking the derivative of vectors, we need to record in which frame we are taking this derivative with respect to, okay? So we are going to take the time derivative in the zeroth frame. So what we're going to have to write to do that is, for the first loop equation, for example, I have to write d dt in the zeroth frame right here of p04 plus p42 plus p20 equals 0. Let's continue with this equation. So in order to take the derivative of this loop equation, of course, I have to take the derivative of the left-hand side of the equation and the right-hand side equation and equate them to each other. Of course, the derivative of 0 is 0 in any frame, but the derivative of the left-hand side is a bit more complicated. Okay, let's try to walk through that. Okay, so we have first of all, we need to understand that the derivative operation is linear. So whenever we have a summation of various vectors and we apply the derivative to a summation, then we can apply the derivative to the individual vectors and then sum. That comes by the linearity of the derivative operation. In mathematical terms, what I said corresponds to the fact that the above equality is equal to this equality that I'm writing currently. Okay. So the first thing we should notice is this vector p2, p42, that is fixed in the zeroth frame. If a vector is fixed in the zeroth frame and we're taking the derivative in that same frame of this vector that is fixed, of course, since it is fixed, then its derivative with respect to time must be 0. If it is fixed, it must have no velocity, okay? So what we can do is immediately get rid of this whole term on the left-hand side. Okay. Now, we need to analyze what this vector p04 and p42 looks like. So let me go back up to the figure and check them out. Okay. P04 is the vector that goes from the origin of the zeroth frame to the origin of the fourth frame. So that vector is not fixed in any frame, unfortunately. But a good thing about that vector is it is always in the y1 direction, or equivalently, it is always in the y4 direction. Okay, so since at least its direction is fixed, so it makes sense for me to take to move that derivative from the zeroth frame to a derivative in the first or the fourth frame. And I know how to do that. I do that by using the differentiation in two frames formula. And if we look at the vector that goes from the origin of the fourth frame to the origin of the second frame, this is for p42, That vector is literally fixed in the second frame, so clearly it is beneficial for me to take that derivative in the second frame. So I'm again going to use the differentiation in 2 frames formula, but this time I'm going to move the derivative from the 0th frame to the second frame. Okay, so that was a mouthful. Let's go back down and apply them, okay? So here, what I said was, I am going to take the first derivative, either in the first frame or the 4th frame. Let me take it in the first frame. This is going to be the derivative of the vector from P of the derivative of the vector P04 in the first frame, plus the correction factor, of course, says angular velocity of 1 in 0 cross P04. Okay, this is the differentiation in 2 frames formula. This is, of course, equivalent to this first term here. Okay, equals. Now, plus the derivative of the vector P42 in the first frame. We said that we would like to take that derivative in the second frame, more than we do in the 0th frame. Again, I'm going to use the differentiation in 2 frames formula to go to the second frame. And then I'm going to get this equation. Okay? Very good. Now, the vector P42, that's right here, that is fixed in the second frame. So the simplification immediately is that this term is equal to 0. Very good. So we are left with 3 terms. And the derivative with respect to time in the first frame of the vector P04, we can easily compute that if we express P04 in the first frame. But what is P04 in the first frame? Let's go back up to the figure. P04 is the vector that goes from the origin of the 0th frame, that is from O1 to B, right? That has length D4, and the direction, its direction is Y1. D4 is a variable, of course. So the vector P04 in the first frame is clearly D4 Y1. Yes, D4 is its magnitude, Y1 is its direction. So I can carry on and put that in here. This is d dt in 1 of what? D4 in the Y1 direction. Angular velocity of 1 in 0, if you watch our previous video about how to compute angular velocities, this angular velocity is going to be equal to theta 1 dot in the z1 direction, cross P04, of course, I've just written P04, that's here, D4 in the y1 direction, plus angular velocity of 2 in 0, again, I recommend you to watch the previous computing angular velocities video. This is equal to theta 2 dot in the z2 direction. Cross, what is P42 in coordinates? Let's go back to our figure. P42 is the vector that goes from B to O2. Its magnitude then is A2. And its direction is, of course, not Y2, but just the opposite of Y2. It's negative Y2. So what I can do here is, for P42, I can write negative A2 in the Y2 direction is equal to 0. Very good. Okay, let's look at this again. We can even further simplify this. Now I want to take the derivative of d4y1. That is a multiplication right there. d4 multiplies y1. One of them is a scalar, the other one is a vector, of course. So in order to take the derivative of a product, I need to use the product or the Lightness rule, which says take the derivative of the first term here times the second term plus the first term as it is and the derivative of the second term. Now, look at this here carefully. When I took the derivative of a scalar, I don't need to record in which frame I'm taking that derivative in which frame I'm taking that derivative. And the reason is that scalars don't change depending on which frame you express them in. A scalar is the same in the first frame or the second frame or the third frame or the nth frame, whichever frame it is. So when you take the derivative of a scalar, you don't need to record which frame you're taking that in. However, when you're taking the derivative of a vector like we do here, I still need to retain the frame in which I'm taking that derivative, which was of course 1 in the previous step, so I just carried that over. Okay, let's keep on going. Then the next term here, right here, is a cross product of two vectors. And those vectors are expressed as a scalar times a unit vector. Of course, when you're doing the cross product of two vectors, which are multiplied by scalars, the scalars all can come out. So I'm just going to collect them together here, d4 times theta 1 dot. And z1 dot y1, sorry, z1 cross y1, this is the k cross j term if you recall, that is equal to negative x1. Right, so I can erase this plus sign, replace it with a minus, and put an x1 here. Similarly, for the next term over here, I have theta 2 dot z2 cross minus a2 y2. Now I can take the a2 theta 2 dot term, because those are scalars, in front. I'm left with z2 cross negative y2. So z2 cross y2 was equal to negative x2. Since I already have another negative, this is going to be positive x2 equals 0. And finally, I'm going to do some more simplification. The dt of d4 is succinctly written as d4 dot. And then plus this term right here, let me show you. This term right here, this term, is what? It is actually equal to 0. Why? Because the y1 axis is one of the axes that are by construction fixed on the first link. We assign those frames, or we assign those vectors such that they are fixed in that frame, on that link or in that frame. So it must be that since the vector is not changing at all in the first frame, this must be the 0 vector. So I don't need to write that. But if I keep on going, this is going to be d4 dot y1 minus d4 theta 1 dot x1 plus a2 theta 2 dot x2 equals 0. And finally, I can put everything back in the 0th frame. If you recall, y1 axis had the components minus s1, minus sine 1, cosine 1, and 0 in the 0th frame. d4 times theta 1 dot. The x1 axis had the components cosine theta 1, sine theta 1, and 0 in the 0th frame, plus a2 theta 2 dot. The x2 axis had the components c2, s2, and 0 in the 0th frame. And I will call this the velocity level equations number 1. They are expressed in the 0th frame. That's it. Now let's go back to our star equations, yeah, and take the derivative of the second loop equation, loop 2. How do we proceed? We have d dt of 0, p03 plus p35 plus p52 plus p20 equals 0. Correct? Okay. And as before, I'm going to distribute the derivative over the addition, which is going to give me the sum of derivatives of each term. Bear with me as I write this. Very good. first things first, let's identify what is constant. This thing is constant, as we established in the previous equations. Well, okay, sorry. There was a small mistake here. These are not 4, 2, these are 2, 0. Sorry about that. I may need to add a disclaimer when I post the video about that. Okay, in any case, we said that was 0 in over here in the first part of the velocity level analysis, and we're going to repeat that here. And the reason is that the vector p20 is fixed in the zeroth frame. It's literally going from, if you look at the figure, it's going from the first, say the 0.02, which is a revolute joint, center of the revolute joint, to the center of the other revolute joint, which are fixed to the Earth. So that vector is fixed to the Earth, which means that the derivative of that in the world frame or in the Earth frame is equal to 0. Okay. The derivative of the vector p03 in the zeroth frame, though, I really want to use the differentiation in two frames formula again, because if you look at our figure back over here, the vector p03 is the vector that goes from O1 to C, and that vector is fixed in the first frame. So if I take that derivative in the first frame, then it's going to be easy for me. While we are here, let's look at the vector that goes from the origin of the third frame to the origin of the fifth frame, and that vector is fixed in the third frame. So when I take that derivative, I really would like to take that derivative in the third frame. So use the differentiation in two frames formula accordingly. The vector that goes from the fifth frame, origin of the fifth frame, to the origin of the second frame, of course, is not fixed in any frame, but the direction in which that vector lies is fixed. Essentially, the vector that goes from the origin of the fifth frame to the origin of the second frame will always be in the x5 direction. Only its length is going to change. So that's going to yield some simplifications as well. Okay, let's collect these thoughts in mathematical form over here. We said that to do this derivative, I'm going to use differentiation in two frames formula and put the derivative in the first frame. For the second term up here, I'm going to take that derivative we set in the third frame by using the differentiation in two frames formula again. Sorry, I made a mistake, small mistake here again. Sorry about that. This is one. Very good. And we said that the P52 is essentially D5 in the x0 direction. So I can just literally write this as, I don't need to use differentiation in two frames formula because this is already in the x0 direction. Okay, and that's whole thing is equal to 0. Let's move on one more step. Now, while moving to this new step, we recognize that the vector p03 is fixed in the first frame, so its derivative in the first frame is 0. Similarly, the vector p35 is fixed in the third frame, so its derivative in the third frame is 0. Okay. Angular velocity of 1 and 0 we said was equal to theta 1 dot z1 cross p03 was equal to, I believe, a1 in the y1 direction. If you go back to the figure, you'll see that that is the case. Now, angular velocity of 3 and 0 is equal to theta 3 dot in the z3 direction cross p35 is minus a3 in the x3 direction. And the derivative of this term right there, again, requires us to use the Leibniz rule or the product rule, which is going to give me plus d5 dot in the x0 direction. And the reason is that the derivative of x0 in the 0th direction, in the 0th frame, is 0, of course. So the second term has vanished, as it did over here. Okay, let's double check this. P03 is the vector from O1 to C. Its length is A1 and it is in the Y1 direction. That was correct. P35 was over here, right? It's from the origin of the third frame to the origin of the fifth frame. So its magnitude is A3 and its direction is minus x3. So that is correct as well. So let's do the algebra here. This is going to be A1 theta 1 dot. As we said, scalars can come out. Z1 cross A1, Z1 cross Y1 is going to be minus x1, right? So I have a negative x1 here. Okay, and the positive A3 times theta 3 dot x3 here. Again, I pulled the scalars out or to the left, and then I did, of course, I did it wrong. This whole thing is wrong. Let me do it again. So theta 3, what I'm doing is theta 3 dot z3 cross minus a3 x3. So a3 theta 3 dot can come out. That part is correct. But I need to do z3 cross minus x3. So z3 cross x3 is plus y3. Since there's a minus there, this is minus y3. Very good. Okay, and then the next one is clearly d5 dot in the x0 direction equals 0. All right, so let me put all these in the 0th frame. The x1 axis in the 0th frame is going to look like minus a1 theta 1 dot. That's going to look like cosine 1, sine 1, and 0. These are its components in the x0, y0, and z0 directions. And the it here is the x1 axis. Minus a3 theta 3 dot, the components of the y3 axis in the x0, y0, z0 frame. What's it going to look like? It's going to look like minus sine 3, cosine 3, and 0. Yep. Very good. And of course, the components of the x0 vector in the x0, y0, z0 direction is 1, 0, 0, right? So this is going to be plus d5 dot 1, 0, 0 equals 0. And this one here gives us velocity level equations number 2. All right, let me end this video here because it has already been taken quite a long time. I want to end it here, and then in the next video, I want to put these equations in matrix form and solve them.